Poisson distribution as a limiting case of binomial distribution. So why we deal the Poisson distribution as a limiting case of binomial distribution? We have the following conditions here. The first one is n tends to infinity. N is the number of trials in the binomial distribution. When it is infinitely large, we will come to Poisson distribution. The second condition is p tends to minus infinity, which is probability of successes in the binomial distribution. When it is tending to infinitely small, we will come to Poisson distribution. And the third case is np, the mean of binomial distribution, is equal to lambda, which should be a constant. Whenever these three cases are satisfied, we will come the binomial distribution will be treated as a Poisson distribution. Now we will have a student to perform this limiting case here. Now we have a student to explain the Poisson distribution as a limiting case of binomial distribution. What is our first condition? N tends to infinity, which is the number of trials is tending to infinitely large value. What is the second condition? What is P? P is the number of successes. P is the number of successes. When it is tending to infinitely small value, we will go to the Poisson distribution. The third condition is
NP equal to lambda is a constant.
NP is equal to lambda, which should be a constant. Whenever these three conditions are satisfied, we will take the binomial distribution to be a Poisson distribution. Now we are going to derive the moment-generating function of Poisson distribution, for which we are in need of the probability mass function, since the Poisson distribution comes under discrete random variable. So what is the probability mass function of a Poisson distribution? Probability of x is equal to x is equal to e power minus lambda into lambda power x by x factorial, and x values will likely to be 0 and infinity, and your lambda is a parameter. This is the probability mass function of a Poisson distribution. So under this we are going to derive the moment generating function. The first condition is moment generating function, which is equal to, we will represent it as mx of t, which is equal to summation of x is equal to minus infinity to infinity e power dx into p of x. Here the p of x is the probability mass function of the Poisson distribution. Now the second line for just replace the p of x with the probability mass function of the Poisson distribution, which is e power dx into e power minus lambda into lambda power x by x factorial. In the second step, we have just plugged up the power of x here. And moving to the next step, we have got e power minus lambda as a constant, and we have taken it outside the summation here, and we have expanded the bracketed term here. And also, we come to see that e power x values are represented in this bracket, and therefore we have replaced x with e power minus lambda t, e power lambda t. So we have our mx of t to be e power lambda into e power t minus 1. So this is our moment generating function of the Poisson distribution. So what is the moment generating function of a Poisson distribution? Mx of t is equal to e power lambda into e power t minus 1. Now we are going to see the mean of Poisson distribution. Now we have a student to say the formula to find the mean of a Poisson distribution.
Mean of Poisson distribution, mean equal to E of x equal to mx dash 0.
Mx dash of 0, which means we are going to differentiate the moment generating function and replace t with 0. Mx dash of t, we are going to find the differentiation for mx of t, which is mx dash of t is equal to e power lambda into e power t minus 1, and in place of x we have lambda into e power t minus 1, and on differentiating it we have lambda into e power t. On simplifying it we have lambda into e power lambda into e power t minus 1 into e power t. Now we are in need of mx dash of 0 only, so we are replacing t with 0 in the star equation here. On replacing t with 0, we have this term to be 1, this term to be 1, and therefore the final value of mx dash of 0 is equal to lambda. Therefore the mean of Poisson distribution is lambda. Now we are about to learn what is the variance of Poisson distribution. Now we are going to learn variance of x. What is variance of x for Poisson distribution?
X equal to E of x square minus E of x whole square.
And what is E of x square?
M of double dash x over t.
Mx of double dash of t is the formula to find E of x the square. Thank you. Now we are going to find mx double dash of t using the star equation. We have already mx dash of t, and again we are going to differentiate it again here. So what is mx double dash of t? Lambda into considering this term to be u and this term to be v. We are going to differentiate it in the uv formula. What is uv formula? D of uv is equal to uv dash plus du dash. Differentiating of t 0. Therefore, we have lambda into, for the first term, when we substitute t is equal to 0, this term will become 1. When we substitute this t is equal to 0, this term also will become 1. So 1 into 1 will be 1 here as the first term. Plus second term is e power t into e power lambda into e power t minus 1, which means here also if we substitute t is equal to 0, we will have 1 as the final term into this lambda into e power t. Lambda is a constant, so we are just giving it as such. And e power t, e power 0 is 1 here. That is why we have mentioned it as lambda for that. And on simplifying it, we have lambda into 1 plus lambda. And on expanding it, we will have lambda plus lambda squared as value of e of x squared. Now we are in need of finding the variance of x. What is the formula to find variance of x? E of x squared minus e of x the whole squared. What is e of x squared? We have found it as lambda plus lambda squared minus what is e of x squared? We have found as mean. Mean is e of x. E of x is the whole squared is lambda the square. So we have written it here. And on cancelling it out, we will have variance of x to be lambda. So finally, we have derived the monogenetic function of Poisson distribution with the help of the probability mass function. So we have found the monogenetic function of Poisson distribution to be e power lambda into e power t minus 1, and its mean to be lambda and its variance to be lambda. So this is how we derive the parameters of Poisson distribution. Now we have a student of AML to explain the design thinking approach on Poisson distribution. The distribution of Poisson and its properties have been already explained in the classes, and now we will have the design thinking approach of the Poisson distribution here.
Okay, good morning all. So today I am here to discuss about Poisson distribution under 5 pillar concept. So the 5 pillar concepts are empathy, ideate, defend, prototype and test. So here is an empathy. Telecommunication company operates a call center where a number of customers arrive. So they not have an efficient servers to manage the call center. So that's what the empathy here, to handling incoming calls without excessive wait times. So they came up with a definition of Poisson theory. So the Poisson distribution is used in model of numbers of calls arriving in a fixed time period. So if the average number of calls per minute known, for example, 10 calls per minute means a Poisson distribution to predict likelihood a specific number of calls in a given time. So we have some use cases. So this is what define the idea. So estimate the probability of receiving more than 50 calls in a minute. So they determine that the minimum number of agents required to keep the average waiting time. So with an ideate of 1500 call minutes, then they optimize the staff during peak and off-peak hours. So based on call, so we have a test case formula. To x presents the number of calls received and the minute average and the number of calls they will 10. So the final output from this, the company can use Poisson modeling to avoid understaffing needing of a customer business and overstaffing to more reliable to use.
Thank you for the student who have explained the design thinking approach on Poisson distribution, wherein we have explained all of the 5 pillars very cleanly and precisely.